All right. Good morning, everyone. Looks like a few people might be lagging here a little bit this morning, but we'll see if they pop in. Get stymied by the clouds again. I went to look for the comment. No good. So keep trying this week if you're interested in that sort of thing. So let's see. Today's going to actually just be a lot of very little theory and just a lot of examples. I think there should be plenty of time for questions, plenty of time for you to work on homework, maybe to get caught up. So 13.1, 13.2, they kind of come together here. So we did 13.1. That's a way of going from one integral to another. We showed that, well, let's see, that if you're doing these double integrals, at least the one thing to keep in mind is that if you see this symbol, then you don't have to really know, you don't have to know anything except for the fact that this means that this is the area of R, where R, again, R is a region in the plane. So instead of just having your brain like tick over and go, oh, I got to figure out all the bounds and integrate, no, it's just whatever the area of this thing is. So if it happens to be a circle or a rectangle or a triangle or something, you don't have to do any work, you just use the formulas that you already know. So that's pretty nice. Now, just as a recall here, in general, when we're doing these Riemann sums from before, you can't get rid of these things, you can't avoid them. The old process, again, is you were given an interval from A to B, and you're given the function y equals f of x. The function could go, well, I'm going to draw it this way. So the function could start and go below the axis, and I think I might have to separate my cats here. Sorry about that. They've been good for a while. Now they decided to go crazy. So what we did before was we took A to B, we chopped it up into a bunch of little pieces, and on each of those we approximated the function using a rectangle. So we could either use the right-hand method, the left-hand method, or the midpoint. It doesn't end up really mattering in the end because we're going to take a limit on this stuff. So, so we put in our rectangles, and some of the rectangles are above the axis, and some of them are below the axis, and that's okay. And so then what we did is we found the area of all of those, and what we meant is we meant the signed area. So that could be, it could be plus or it could be minus if it's above the axis, and it's minus if it's below the x-axis. But all of these areas are just length times width, or in this case, they would be the function value at a specific point, and we would multiply by the width of each of those little strips. Assuming they're all the same width, we could just use delta x for the width. And then we added all these things up, and then we took a limit as the number of rectangles went to infinity, or you can think about it as the width of the rectangles went to 0. So both of those things mean the same thing. And we would end up getting the symbol A to B of f of x dx. Or if I want to use my notation that's in mind, well, maybe we've never seen it, but it's not a bad thing to keep in mind. And what that meant, and this is sort of basically the only new thing for 13.2 is to give a meaning to this in more general, is this was the actual total, put that there, the total signed area under y equals f of x. And it could be 0, it could be negative, it could be positive, it could, 0 would be if the graph was perfectly symmetric, for example, and if the top area and the bottom area ended up canceling each other out, you could get 0. That would happen with actually any odd function, um, because that has rotational symmetry. Anything on the top is going to be balanced by anything on the bottom. As long as you integrate from this, like -2 to 2, they would cancel each other out. So how do you do this exact same thing in 3D? Well, it's a little trickier, and now you're in 3D. So when you plot these things, so I'm going to do X, Y, Z this way. I'm going to be given a function, not Y, Z equals f of x, y, and I'm going to be given a region R in the XY plane. And that could be, now, I mean, intervals are easy. You just go A to B. But now you have a region that could be any blob shape you want. It could be a rectangle, could be a triangle, could be a parabola, could be, or it could just be some shape here. So there's my region R. And where is Z equals f of x, y? Well, these are surfaces that are on the z-axis. You think of this as an elevation. So it could be a paraboloid, it could be a sphere, it could be a plane, it could be anything. It could go above or below the XY plane. It could cut through. These are where your imagination, you have to be pretty good at seeing what these look like. So in general, if I wanted to draw a surface, I just kind of draw it's like a blanket here. So Z equals f of x, y, and that's just part of it. It's typically, it goes out infinitely far, or it could be a sphere and it stops. Then just like before when you're talking about the area under the curve f of x, now we're going to be talking about the volume under this surface. So we want to talk about the volume under the surface, but above R, above the region R. So R is kind of like going to be like the shadow of what we're talking about. So if you can see this, here's what I mean. Just like before, you take your interval and raise it up to the function. Now we're going to take our curve here and we're going to raise it up to, it's not bad. So you raise that up until you hit the surface. Then you're going to be getting this sort of weird 3D shape underneath it. And I'll draw a few more lines here. I don't know. Maybe I'm just cluttering the picture, but it's kind of, so I don't know if you can see that or not, but you end up getting a volume in between those two things. If the surface went through the plane, you would have part of the volume below, and you'd have part of the volume above. So really, and I probably won't write this very much, but you can think of this as the signed volume. So it could be positive, it could be negative as well. So how do we do this now? Well, guess what? Here's what we do is we take our region in the XY plane, and maybe I have it turned, but that's all right. And you chop X up into little pieces. So each of those little things are like delta X. You chop Y up as well. So we're going to do like a double Riemann sum here. But these are all delta Y, and so you're going to end up getting this like grid. And for most of the cases, we're not actually going to end up doing any of these. You could. It's good practice, I suppose. But just like for the Riemann sum before, what do? Well, I take these and I lift, maybe I'll just come back up here. Now my grid lines look like this for Y, and my grid lines look like this for X. And then I'm going to take each of these individual little squares, maybe I'll change the color here. Take one of these individual squares, and I will lift that up to get like a pillar, like a rectangular pillar. For every single one of these little squares. Now you're like, well, what about the things that overlap? Well, or don't, like they're not complete squares. Well, that's where it's just like in the Riemann sum before, you missed a little bit. Maybe your rectangle overestimated or underestimated. So we might, we're going to be missing some stuff around the edge. But then we just take this and we add up all the volumes. okay, not 2 feet. Add up all the volumes of the pillars. And they're just, they're just prisms. So the volumes are just going to be like, width times length times the height of all of those things. So what does that mean as far as what are width and length and height? Well, the height is going to be governed by the z, and the width and the length are going to be governed by the delta x and the delta y. So we can add this up. Let's see. So it'll be the width, which is like delta x, the height, which is delta y, or sorry, the length is delta y. The height will be a function value at your specific point. It's just like, how do you do this now? It's like left endpoint, so I'm at one of the corners, or do I take the midpoint of all of these things? It's like, again, it's a double Riemann sum, so they'll often write it as I add up on the x's, and then I add up for all the y's, and that will be volumes, just length, width times length times height. And you can add it up this way, or now here's sort of the new one, is you can add it up. It's gonna end up looking exactly the same when you write it as writing the length times the width, or the width times the length. When you're adding them up for y and adding them up for x, they'll look exactly the same. You'll get exactly the same answer. But the reason I write it like this is because when you take the limit of these things, so now it's the limit as delta x and delta y gets smaller and smaller and smaller and smaller, and you get infinitely many pillars inside of here. Same thing down here. Take the limit. You'll either get a double integral over the region of your function dx dy, or you'll get the double integral over the region dy dx. And they'll be the same because they both represent volume. And in either case, you'll write the double integral over the region dA. That'll be like the shorthand for it, whether you want to talk about integrating for x and then y, or y and then x. And we did a little bit of that stuff set up already, but the key is that we're talking about that this represents signed volume now. So that's all. So there's your theory for the day. Now we're just going to do a ton of examples. And a ton means, I don't know, 5 or 6. And then see if you have questions about homework and stuff. So for example, we could say, find the volume under this curve, x plus y plus z equals 1, in the first, you can't say quadrant anymore, because in 3D, you chop it in, you're chopping it into 8 pieces. So this is called the first octant in space. Octet, it's not a singing group. So that's where x, y, and z are all positive. So yeah, I don't want to go off too much on a tangent, but like back in 2D, this is the first quadrant. Where is the second quadrant? So if you didn't know, if you didn't know anything about, where the quadrants were, I don't know which way you would go. Maybe you'd be like, well, this is the first quadrant, and of course we go clockwise. So this would be the second quadrant, this would be the third quadrant, this would be the fourth quadrant. But somehow someone said, nah, we like to go counterclockwise. So this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. And that's totally arbitrary. I think 1 and 3 probably make sense, like where x and y are both positive and where x and y are both negative. But why this is the second quadrant and this is the fourth, or vice versa, there's kind of no rhyme or reason to it. And if you think I'm talking crazy, then what about in 3D? So now you've chopped it into, there's like 4 quadrants above the XY plane, and there's 4 quadrants below. And I shouldn't say quadrants because there's 8 of them. There's octants. So if you had to label all of the 8 octants, I have no idea what the answer is. I think the first octant is, I mean, when we write X, Y, and Z, we really mean that these are like the positive, the positive X, Y, Z. So that block up there is typically called the first octant. But I don't know what the ordering is on any of the other ones. So I don't know how you do it. You go around this way, maybe you go back around this way, 1, 2, 3, 4 on the top, and then what do? Drop down, go 5, 6, 7, 8. I don't know. I'm not even sure there is a thing on that. So this is, you know, again, lots of things in life are actually arbitrary, and people just picked it and said, that's what we're doing. Why do we drive on the right side of the road? Well, we picked it. Why do we read left to right? Well, someone just said that's the way we do it. Could we go up and down? Yeah, and there are languages that go up and down. So I don't know. I mean, we just picked one and stuck with it. And that's just the way it is, right? That's just obviously the way it is. Okay, so back to this. So this is a surface. So x plus y plus z equals 1 is a surface. And hopefully that jogs your memory that this is a plane. So we want to draw this plane and see how it relates, what does it look like, and how does it relate to the first octant. So the easiest way to do this is to look at where the plane hits the 3 coordinate axes, so the intercepts. So what I mean is if x and y are both 0, then I'm going to get the x-axis intercept. Or just, maybe I should just say the x. I'm going to get x. I'm going to get the z-axis intercept or the z-intercept. And that will be z is equal to 1. So I know for sure that I hit at the point 0, 0, 1. And that makes sense. I can plug in 0, 0, 1. If I plug in x and z equals 0, then I'll get the y-intercept, and that will also be at y equals 1. And they're actually all at 1, just because, you know, you can solve the equation. Plug 2 of them in to be 0, and the third one is going to be 1. So that means that if the plane hits at 1, 1, 1, and the plane will come through slanted that direction. And when it hits, it has to hit, you know, it has to hit in straight lines. So what I'm talking about is that is where it hits. That's the part that's in the first octant, and I want the volume underneath it. So it's like a triangular prism. It's, you know, the back, this is one face, that's one face, this is the bottom face, and then you have this front face on it. And so it's all the stuff that's inside of there. So it's kind of like, yeah, it's part of a cube, really. It's a 1 by 1 by 1, and you kind of slice part of the cube off, and it gives you that that part, that sort of triangular prism part. All right, so there's a lot of writing on there. But the point is that the volume is going to be given by, well, we need z as a function of x and y. So we first get z by itself, and then this is going to be fxy. So that's the thing I'm going to integrate. The region, and this is the hardest part typically on these problems, is what is R? What is the region you're talking about? And so I don't know if it's easy to think about it. R is the shadow in the XY plane. So if you, or you can think of it as perspective. If you looked from the top, you projected a light down, and where is the shadow down in the XY plane? And this takes a little, you know, takes some practice, but maybe you can see, you know, R is the shadow down below here. And if we just draw it in the XY, it hits Y at 1, it hits X at 1, and so there's the R, there's R right there. That's the region. It's a triangular shape. It's the bottom of my triangular prism here. And so the volume will be equal to the double integral over that region of 1 minus x minus y dA. And that's at least the setup. And sometimes the setup, well, in this case, the setup's going to be a lot easier than actually doing the integral. So this is key, is to figure out how to convert this for this region. So we have to go back to 13.1. I'll recopy it on the next page here. So I need the volume. It's going to be the integral 1 minus x minus y dA, and my region looks like 1, 1. Here's my region 1. So how do I figure out the bounds? Well, the problem is I couldn't just say, well, 0 to 1 and 0 to 1 for x and y, because 0 to 1 and 0 to 1 would give me the entire square. So that's no good. So I have to find either y bounded by the curve, by two curves, like what is y between, and then what is x between for those curves. Which numbers is it between those two curves? So you look at this, and every y value in here, looking up and down, will always be below the line and above the x-axis. So I need to know what the equations are of the line on the top, and I need to know the equation of the x-axis, and that's just y equals 0. So I know for sure that y is bigger than the x-axis, that's at 0. What is this line here? What is that diagonal line equation? Well, it's a line. So it's y equals mx plus b, and y is, what's the slope? You go down 1 and over 1, so the slope is negative 1. And what is the y-intercept? Well, it's already there, it's 1. So the answer is y is equal to negative x plus 1, is that diagonal line. And because the shaded part is below the line, you would say that y is less than that curve. So below in the picture means it's less than when you write the equation out. If you can figure out that part, then, for which x values am I talking about? Well, x in this picture is only going from 0 to 1, and that's exactly, that's the bounds for x. So that is the characterization if you look at the curves up and down, and you look at the numbers left and right. We're going to do this in both directions. So what you could instead is you could think of x is between two y curves, and then what values of y are you between those two y curves? This is typically a little harder because you've been used to thinking y equals f of x, y equals f of x, y equals. Now we're thinking x equals g of y, x equals g of y, x equals g of y. So when x is between two things, that means it has to be to the right of one curve and to the left of the other. So we need to know side to side here, what two curves is x between? Well, hopefully you can see it's between the y-axis and the line. So the y-axis is just x equals 0. And this line, now I got to convert the line from y equals negative x plus 1. I have to convert it to x equals something. And in this case, it's not too hard to see. You just switch the locations, and you'll get x equals negative y plus 1. And so then that goes into the curve on the right. So because it's on the right, that means that in the equation, x is less than it. X is less than that. And very similar, what are the y values? Well, y is just going to 0 to 1. So those are the two different setups for the region, which means that if you then want to actually calculate your volume, you can use either one. The volume will either be the double integral where the inside goes from 0 to negative x plus 1. The inside's still the same. It's because you're still the same. The thing that's inside is the surface that's above it. So that won't be altered by the actual region itself. It's above this. It's above it. And then this would be dy. And then we do this iterated integral where we do the inside integral for y, and then we do the outside integral for x. So dx in 0 to 1 would be the bound. So that's the setup for one version of this. Or if you want to think the other direction, and sometimes you actually need to, we'll see some examples of that. This will be the integral from 0 to negative y plus 1 of your function, 1 minus x minus y, dx. And then you take that and you iterate it with a dy integral from 0 to 1. And that is the second setup for how you calculate this. That's the hard part. That's typically the hard part. Anything from here on out is just, if you make a mistake, it's just because you screwed up the integral. And that's easy to do, but that's Calc 2. So this is the new stuff. Calc 3 is in the past. There's a lot of theory that goes into this, why you can actually do it this way, why you can switch these and change all the curves around. We're skipping all that abstract stuff, but I'll at least tell you that this is, the fact that you can do this is due to an Italian guy named, he's got the great name, Fubini. So Fubini's theorem, if you want to look that up, says that this volume, this integral can be calculated either way. And there's a lot of math that goes into why this actually works, but you know, we skip all those hundreds of years of math and just give you the answer. Calculating this out, I mean, it's not trivial to do because it's just keeping track of lots of negatives and squares and stuff. But just for kicks, we'll just calculate one of them. You'll get the same answer because they both represent the volume. I don't know if you know the answer to this. Like if you took part of a box, you know, 1, 1, 1. So if you took the entire box, then you know, if this was 1, 1, 1, everything was 1, this volume would be 1. This volume right here of this sort of triangular part, what is that? Is that going to be like a third of the answer? Because have you taken a third of the cube, or is it? I don't think it's half. Well, you know, because what is a triangle? It's like 1/2 base times height, but maybe it's like 1/2 in every direction. So maybe the answer is it's an eighth of the answer. I don't know. If you know the answer to that, great. I'm not sure I've seen that without calculating it out. It's not one of the ones I have in my memory. But it doesn't matter because I can just go ahead and calculate it. 0 to 1. But I would at least take a guess. Is it like a quarter? Is it half? Is it a third? Is it an eighth? I don't know. Figure it out. So we'll do this one. Negative y plus 1. 1 minus x minus y dx. Let's do the x first. We're not used to doing x first, so we'll do it. Well, maybe we are. I don't know. So we integrate this thing with respect to x. And so anything that's y is going to think it's going to be like a constant. So the 1 integrates to x, the x integrates to 1/2 x squared, and the y integrates to negative xy. We're doing an x partial integral here. I want to evaluate that between, and here's where it's not a bad idea to say, where do I plug in the bounds? And these are x bounds. So we plug in x equals 0 and x equals negative y plus 1. And then subtract. Well, I mean, clearly when I plug in 0, everything is going to be 0. So the only thing I really have to worry about is plugging in this top bound. So 0 to 1, I plug in negative y plus 1. That goes in for x. Negative 1/2, okay, negative y plus 1 squared. So there's an easy place to make mistakes. And then negative x times negative, or sorry, that's why I'm plugging in x here. Negative y plus 1 times y. I don't need that parenthesis there. Okay. And then I have to integrate that with respect to y. So I don't know if you want to multiply all that stuff out and then integrate each one, or do some like little u substitutions, or I don't know. This is very easy to make lots of mistakes. 1, 2, 3, 4, 5 different minus signs you can screw up on. So anyway, I'm going to let you do that. This is for you. It's not hard. And the answer is, drum roll, it's actually 1/6 units cubed is the volume. So now you can maybe put that in your brain, and if you take a cube and slice off this bottom corner, it's actually 1/6. So you could like fit 6 volumes of these worth in the cube. I don't know if that makes sense or not, but it looks too big. I don't know, but anyway, that's one example. the long version. All right, so let's do a couple more here. Maybe we'll do one more and then take a quick break. So here's, for example, what is the volume under z equals 1 minus x squared. It's under this above the xy plane. I don't want it to go negative here. And only for y going from 0 to 2. So it's not going to be as simple as like, hey, find the volume under z equals 1 minus x squared, because you're going to be like, well, all of it? That's going to be like negative infinity. Okay, well, I got to constrain it a little bit by putting in more conditions. So let's see what this thing looks like. We have to remember what it looks like. Z. Okay, so what does it look like? It looks like a parabola, except it's not a parabola in 3D because I have to draw this 1 minus x squared for every y value I have. So this ends up being like a parabola stretched out along the y-axis. So it does hit here at 1. It does hit here at -1 and -1. So it does look like the parabola that you would expect. Except now it stretches out because there's no y constraint in the equation. It's going to look like that parabola all the way out. So parabola. It's supposed to come all the way up, and then this comes all the way out this way. So we're going to get rid of a little bit. So it would extend in both directions forever. So it's this parabolic, like, you know, gutter or a trough or something that's like upside down. And we want it above the XY plane, so we have that. And we only want it to go out here to where Y is 2. So if I chopped it off at 2 and put in a few more curves here, it looks kind of like airplane hangar maybe, or not. It might be a little, I don't know. What does that look like? A bunker of some kind, or a really bad mailbox that's been squashed? But the question is what is the volume of that sort of airplane hangar? And the answer is, well, it's going to be equal to the double integral over a region of 1 minus x squared dA. That's the application for today, that is the volume equation. How does that resolve out? Well, you need to know how to convert R into specific bounds. So what is R? R is going to be the shadow of this down in the XY plane. And maybe this one's not too hard to see, is that if you did look at the shadow, X is going from -1 to 1, so -1 to 1, and Y is going from 0 to 2. And it's actually a square. It's 2 by 2, so you do get that square. Which means it's as easy, this is now super easy, is if it's a rectangle, it's just the integral. If you did Y first and then X, Y is going from 0 to 2, and X is going from -1 to 1. Or if you prefer, if X went first, well, again, X is going to be -1 to 1, and Y is going to be 0 to 2. So if you have a rectangle or a square, it looks like you can just switch the bounds, and you really are. But if you think about it, the things in the first, this outside integral are actually numbers, like y equals 0 and y equals 2, just numbers. But these inside ones here are really like, these are curves, or they're lines. So you can think of, you're going from the line at 1 to the line at, or -1 to the line at 1, and then for the numbers from 0 to 2. So it's really, these look like they're numbers, but in 2D they're actually lines. So it should always be curves on the inside one and numbers on the outside one. So that's not too hard to evaluate. So probably even we'll just leave the evaluation to you, but realize that in the end you're going to get a volume, so it's going to be units cubed. So whatever you get, it's not just like the answer is 6. It's, well, 6 what? 6 cubic feet, cubic meters, cubic whatever your unit is. All right. Yeah, let's take a quick break there, I think, and come back. We'll do maybe 1 or 2 more like that, and then really these just are just practice. It's a lot of good practice. Drawing the pictures, looking at the shadow, describing the shadow in terms of curves and lines, and then evaluation. The evaluation I don't really care as much about because that's all Calc 2 stuff. But anyway, all right. Come back at 8, I don't know, 5 minutes from now. So see you in 5.